Hi there, my name's Jacqueline Halpin. I'm a geologist at IMAS. My work's taken me to Antarctica. Here I am, one of these little yellow people down here on the right hand side of the slide. I've been there to map the geology and collect rock samples to help piece together what lies beneath all that ice. Antarctica is really planet Earth's last great frontier. It's a continent about 1.7 times the size of Australia, and there's really only less than 1% of bedrock exposed at the surface. In recent years, our vision of the continent has shifted dramatically. Aircraft fitted with ice-penetrating radar reveal a spectacular topography of rugged mountain ranges, steep valleys, deep lakes, and river networks. One of the surprises in the interior has been the Gamburtsev subglacial mountains in this region here. They cover a region about 700 by 250 kilometres, so the size of the European Alps. And this radar image shows what's underneath all that ice. You can see the layering within the ice sheet here, mimicking the peaks and troughs of the bedrock below. The highest peak is about 2.8 kilometres above sea level, and the deepest valley is about 800 metres below sea level, and all of that is hidden beneath kilometres of ice. That landscape is originally thought to have been carved by rivers, and you can see those river networks in this image over here. And this area is really important for a number of reasons, but one of them is that the mountain range is thought to be the key starting point for the ice sheet that eventually spread across the whole polar region about 34 million years ago. It started here in the Gamburtsev Mountains. So how did this rugged continent form? Well, here's an Antarctic-centric view of planet Earth today, or as geologists say, 0 million years ago. So here's the time period up here. But of course, the Antarctic continent hasn't always been stranded at the South Pole alone and surrounded by ocean. I'll play this tectonic reconstruction movie now, and we'll go back in time and see Australia, India, Africa, South America all move south and join to Antarctica within Gondwana over some 200 million years before present. The pictures here have modern day topography and a modern ice sheet. They're not relevant as we go back in time, but I've left them on just so that you're able to orientate yourself more clearly. So we'll start this now. So we're going back in time here. You can see time marching back up in the top left corner. You can see Australia moving towards Antarctica, India coming in quite fast there, Africa, South America. You can see the ocean floor slowly disappearing as we go back in time, and some reorganisation of parts of West Antarctica over here as well. All the way back to about 200 million years is where I've stopped this reconstruction. I'll just stop that one. Okay, so this is the configuration of Gondwana, and that's quite well accepted these days, and that's because the ocean floor records a magnetic signature that allows us to map the age of the ocean floor, and then we're able to systematically remove that ocean floor back in time to create the reconstructions that you've just seen. But what if we want to go further back in time? If we want to go beyond Gondwana? And we know that through deep time, through the process of subduction and continental collision and rifting, the face of the planet has been constantly changing. So how did the pieces of Antarctica actually come to be? They formed Gondwana sometime between 700 and 500 million years ago. So here's a global reconstruction that looks at that time period. We'll play that now. So you can see here time marching forward this time. We've started at 700 going towards 500. You can see bits of Antarctica, part that's connected to Australia, part connected to India, part that's connected to the Kalahari, and other parts that just seem to sort of turn up unexplained during the reconstruction. And that really reflects how poorly understood the interior of Antarctica is, and how much more work there is to do. So these global models are a start, but how do we understand the evolution of Antarctica through deep time? And what about the processes that have shaped the modern continent, or how the underlying geology continues to influence the flow of ice, both above and the oceans surrounding Antarctica? So what are our touchstones? What can we hold on to as some kind of truth? Well, geoscientists use a number of tools to probe the continent. Where we can, we use the most accessible outcrops and we sample rocks directly, bring them back to the laboratory. We're able to analyse all sorts of things, their mineralogy, their chemistry, their age. And we can also use the ice sheet as a sort of transport hub. So this image shows the ice sheet velocity at the surface, slow in blue and fast in red. And the fast-moving ice streams and glaciers transport moraine material from the interior to the margins and spit rocks out at the mouths of glaciers and along their edges. Icebergs also carve off the front of floating ice shelves, and they take with them sediments from the continent and drop them on the seafloor, where we can collect them in dredges and sediment cores and analyse them. And we can use satellites and airborne technologies to probe the structure and the chemistry of the continent below the ice. And within the last 10 years, with huge international collaboration, these sorts of data sets are revolutionising our view under the ice. So I'll leave us here with the title of the presentation, What Lies Beneath? And here's a beautiful image that I think is quite theatrical by one of our PhD students here at IMAS, Tobias, that combines various geophysical data sets to provide a map of the likelihood of the deep crustal architecture of the Antarctic continent. The brighter shades of white showing where boundaries between different parts of the continent are most likely. So this is really a story to be continued. By combining the various strands of evidence, we can get closer to the truth.